I started recording.
Yeah.
Okay. Oh, sorry.
Yeah, now it's recording.
OK，也、好，那各位贵宾哦，那我们今天是台湾，sorry，我们今天是台湾半导体展的第一天哦，那很高兴我们邀请了美国的2位贵宾，分别是 Vahi 跟 Rick 来帮我们做这样的一个第一场的演讲，然后主要演讲的主题会是利用一种比较特殊的脉冲光的烧结技术，去达到低温烧结的一个目的。好，那我们这边就把时间交给Vahi。Vahi 本身他是Nova Century 的技术长，Rick 是本身是教育训练的经理，所以待会会有大概20分钟左右的时间，我们让 Vahi 来说明一下这个一个很新的一个技术。Yep. Now, yeah. We are very pleased to invite Vahi to present the topic today. We are going to talk using PulseForge tool to soldering component onto temperature sensitivity, subject using standard SAC solder arrays. So I think, it is a very brand new tools. I think that all of us can catch up the idea from Nova Century. Yeah, please go ahead, Vahi.
Thank you, Peter. Thank you, everybody. Good morning. Thank you for joining me here at SemiCon. Unfortunately, we cannot be there in person, but we are there in spirit, and we are hoping that the tech team can provide the best kind of environment for the learning. And thank you, Peter and the team, for setting up this opportunity for us to present from a far away place. My name is Vahi Dakhawan. I'm the technical kind of lead. I'm one of the application engineering leads here at NovaCentrix. And today I want to talk about the concept of PulseForge soldering, with mainly, as Peter pointed out, how do we do PulseForge soldering on temperature-sensitive substrates using kind of standard SAC alloys. So how do we use SAC alloys on substrates that really cannot go through a reflow process? So a little bit about who we are. NovaCentrix is a company. We're relatively small. We're 80 to 90 people now. We're stationed out of Austin, Texas, in the United States. We do have offices in Seoul, Tokyo, Wuxi. We have partners like DETEKT in Taiwan, as well as other places around the world. And we're happy to kind of provide an industry-leading photonic curing system we call the PulseForge tool, as well as inks and powders for print electronics industry. We have a very extensive IP portfolio that provides us a very state-of-the-art capability to get involved in many different projects. So as I was saying, NovaCentrix provides 3 types of products. We have nanoparticle powders that we produce using a very innovative type of technology. We can either use these or other methods to create inks of particles that we can print for functional printing, meaning that the final print allows us to have some ability to do kind of conductivity, resistivity, or some other functionality beyond just the graphics look of the print. And then at the other end of the spectrum, we produce these photonic curing tools that enable us to do a lot of very interesting things, mainly around print electronics world, to get the best value out of our system. These tools are traditionally used to process conductive inks on substrates. So here's an example of kind of a pressure sensor, a door sensor. We used the photonic curing to center the inkjet printed nanoparticles into larger grains for better conductivity. Peter and team can definitely provide more information about conductive inks and how we process them. But kind of so when I say photonic curing, this is the concept of what we're doing. We're just using a flash of light to improve the conductivity of that trace. And as I said, I'm sure Peter and team can provide a very good explanation of what this concept is. But this is a very fast, low thermal budget way of producing very conductive circuits on different substrates without really having to go through an oven. So it enables us to really save on the substrate. So we provide these tools, but these tools can be used for applications beyond what is just photonic, what is just for conductive inks. We can use these tools for applications surrounding liftoff. We use these tools for applications around semiconductor processing and so forth. But today I want to talk about the concept of, well, now that we have the circuits, right, how do we go from a circuit that looks on a rigid board to a circuit that's on a flexible board, right? And we have shown previously that we can print the conductive traces, but really the question to be answered is how do you attach components, how do you attach conventional components onto those printed circuits? And really the question is, how do you go away from these rigid FR4 substrate to a range of substrates that are really feasible for this kind of processing? And so we do have a very good range of components that we really want to use. And in flexible hybrid electronics, the main go-to position for use of to attachment of components onto these lower temperature substrates that cannot go through reflow process has been to use anisotropic conductive adhesives and anisotropic conductive, so ACA and ACP material. These are very good materials. They do work at relatively low temperatures to attach components. But the key factor to keep in mind is that the performance relative to what you get with standard solders is really poor relative to everything that you really want to be able to get. So what the aim here is, the only really downside of the solder paste is that the inability to really be applied on substrates that really cannot go through a reflow process. So how do we overcome that challenge? So to do this, we have come up with a concept to use the photonic curing, to use these flashes of light to subsequently flash in a non-equilibrium fashion so that we can overcome the challenges that are involved with the low temperature solder that we have. I'm sorry, the high temperature solder, right? The inability to run the substrate through a reflow oven with the high temperature solder HTS material that we have. So here's some concepts of the soldering in action. So this is actually a real-time measurement of the temperature. So you saw it happening. Here's another example of it with a different solder, off-the-shelf solder. So you can see that we can get that soldered without really overheating this underlying substrate. And here's an example of a thermal measurement of the same exact application, where we are pretty much pulsing this with pulse of light, quickly heating up the chip, right? The chip that was sitting in a very high temperature, melting the solder paste, and then pretty much cooling back down within that 5 to 6 second time frame that we had discussed earlier. So because the tools are wide area exposure, we can really do this kind of processing on a very large area. So here's a multiple components that are being soldered at the same time. And we can do this for different size components as well, because we are now exposing a very wide range of area. We can find a processing condition that can solder multiple size components onto the substrate at the same, under the same processing condition, under the same pretty much exposure of light. So one, you might say, well, this is really feasible. Sorry, this is really feasible. This process is really feasible with the laser soldering. Yes, we believe that we are very much within the same kind of range of laser soldering. And I'll talk about it a little bit farther down the field. But the main ability here is that we are exposing a wide area at the same time, where laser is exposing a single junction at the same time. That allows us to really take advantage of a lot of the advanced properties that that solder has. One of the main ones that we can use is the self-alignment property that solder has. So solder, when molten in the liquid state, has a surface tension that allows us to self-align components to the circuit. And what you see in this image is that we intentionally misplace these components, and as the solder melts, it actually realigns the components and you get a much higher yield out of it. This is really not feasible with the laser process, because the laser is heating up each of these junctions individually, leading to the fact that this junction, when molten, if it's misaligned, it will actually go farther misaligned rather than come to the alignment. And so we can really do both lateral and rotational alignment based on this kind of process, where we are exposing both leads at the same time. So what are these things good for? So here's an example of a publication, and we have been working on this process for a long time. We started working on this around 2012, 2013. This publication is a collaboration we did with some of our collaborators at the Holt Center, and you can see that this is a thin chip. They were able to solder it very well to a copper track on here, even though there was no exposure of light at the junction. Here's another example of an application where we did a kind of a thin chip, silicon chip, onto a multi-junction circuit. We were able to solder it. Here's an example of component soldering for like LEDs on PET, and even we have done some work on paper. Here's an example of a kind of a large array soldered onto a TPU substrate. So TPU is a very low temperature substrate. It's used as a inlay for variables, and this has become a very important challenge, important kind of market for us, where we can print silver traces that have very good conductivity, and then we can come in and solder those components onto those silver traces on top of TPU that can be then either previously or at that time be ironed into fabrics, enabling us to form a very good circuit. And this circuit enables us to really have a functional circuit that's bendable. So you can see it bend around, you can actually foldable to a large degree. We can fold it here, and then it has water resistance. So you can dip it in a liquid and still be functional. So these things are really, our performance of these types of junctions is significantly better than the previously mentioned ACA material, the anisotropic material, enabling us to do a lot more kind of functionality, get a lot more of functionality out of the film. So here's another example of micro LEDs soldered onto PEN substrate in this case. So this is a silver trace, and we were able to use SAG solder. Here's just an example of where we want to be with our collaboration with the Whole Center, being able to do an RGB display out of micro LEDs. And this is really something that we're striving towards to get really good yields out of its production. So one might ask, so how does the junction look? So yes, now we say we can do these soldering applications, but how does that junction look? So you can look at here, this is a cross section of the LEDs soldered onto PET substrate in this case. And you can see that you have very good fillet formation. You have good vetting of both the copper and the contact on the substrate, on the component. Looking at the X-ray images, there are, it might be hard for you guys to see over there, but there are some small, very small voids, maybe 1 or 2% of volume voids in this junction. But overall, that's very well acceptable for LED applications. We can actually reduce those maybe a lot more than some other applications, but that enables us to form a good junction that's acceptable, that performs really well in that category. So this is kind of the expectation that we have from the junction quality. The one thing to keep in mind that's very important is the formation of the intermetallic. Obviously, we are doing this processing within a very short period of time. So the whole processing from start to end for this sample was 4 seconds. And you can see that you have a very good formation of that intermetallic fingering at the copper solder interface. And you can we can do SCM images and actually do an EDS and confirm that formation is indeed the intermetallic formation at that junction. One item to keep in mind is that because we can heat up and cool down in a very fast time frame, and there's really no hysteresis and no heat buildup in the film, we can really heat up, cool down, and either extend the formation of this intermetallic or shorten the formation of the intermetallic so that we can get a different depths of intermetallic. So here's a depth of around 1 micron, here's a depth of around 4 to 5 microns of intermetallic formation just by extending the exposure time. So extending the length of the soldering step. We can really kind of minimize this intermetallic formation so that we can remove the brittleness in some junctions. So that becomes a very important factor in some applications where the brittleness is a big factor. So there's a lot of interesting functionality that can be added to the soldering step based on how we approach the formation of that the pulse condition. So as I said before, we kind of fit the concept of photonic cured soldering fits somewhere in between what a reflow oven can do and what a laser soldering can do. At this stage, right, we're not saying that every application can be photonically soldered. What we are saying is that photonic soldering is a very good middle ground between these two types of applications where we can complement each other and provide a more holistic approach towards soldering. So just to kind of think about this, right, a reflow oven, right, we're really limited to FR4 and flex substrate, where in the laser soldering, there's a lot of different substrates that lasers could be applied. We're somewhere in between. We can do a very large range. We can do both the stuff that the reflow oven can do, but we can do a very large range of these substrates that are also temperature sensitive that we would like to do. So similarly, for component sizes, right? A reflow oven can do everything. Laser soldering can do only the components that you have direct line of sight to heat up the junction. But we can do various sizes, but we can also do things that are not direct line of sight. So that's an important. We have a lot more flexibility. I won't go into a lot of details in here, but I'm happy to answer any question. But we do have a lot of flexibility in solder and flux to choose things that are off the shelf. We might not have as large a variable space as a reflow oven, but we are definitely not as limited as the laser soldering on this process. Because of the uniform exposure over large areas, our defect ratios are very low, on par pretty much with what you get in a reflow oven, where in a laser process, you have a lot of issues. And we believe that as we're going to smaller and smaller component sizes, this fact that you can have very low defect ratio and the fact that you can take advantage of some of the self-alignment capabilities associated with soldering enables us to really get a lot of value out of the photonic soldering. So I kind of have touched on a lot of these aspects, right? But these are the values that this type of process brings to your SMT line. So if you are thinking about, well, I would like to start a new SMT line from the ground up, is there some process that we can really build in? I would really encourage you to reach out to myself, Rick, and Peter, and the DETEKT team to see if there is a application out there that's similar to what we have already done, and we can provide some feedback on enabling you to further enhance your capability. But really, what we're bringing to the table kind of divide into the fact that we have a very large cost savings in terms of being able to do standardized material, but we can really do new design options and new materials that are really not feasible with a reflow process. And because of the fact that this is a digital process, it has a lot more safety features built into it than what you come to expect from a very hot reflow process where you have a very hot heat source that really is difficult to cool down. So there's some stuff to keep in mind, and as I have said, the processing that we have done, we get really high quality junctions, and we get a lot of benefits that are feasible for a reflow oven, but really not feasible elsewhere. So come to us, we'll be happy to answer that question. At the moment, the product offerings in this category is kind of a standalone soldering tools that we provide. And this enables us to do up to a 30 centimeter by 30 centimeter boards for this application. And then but this is kind of a batch process where you're manually fitting in the components. The next step in the line is an integrated SMT system that we have built. And this enables us to really speed up the process where this can go and fit in line with a pre-existing SMT line and enables us to process larger boards up to 300 millimeters, 30 centimeter width, but as an arbitrary length on the board. So there's a lot of advantages here to allow us to mass produce the SMT process in a larger MP. Here's the contact for the DETEKT team. Definitely reach out to them. They are a local resource for you guys to get answers from. here's my contact information. Again, my name is Vahid Akhavan, and I'm happy to answer any questions. Please send me some emails. Now, I do have my colleague Alex Rose stationed out of Asia. I'm stationed out of Austin, and another one of my colleagues who will discuss more detail, this will be presenting tomorrow night, is Dr. Rudy Gosh, and he's stationed here out of Austin with me as well. And as I said, the PulseForge tools are a very interesting tool set that we have developed for print electronics. But that said, we can apply the same tool set in a very large array of different applications and get a performance that is suitable for additional value out of that kind of process. So with that, I'll take any questions that might be out there.
Okay, thank you. Yeah. Yeah, do you have any question? You can speak in Mandarin or just speak English. Vahid, I think that I have the question for you. Yeah. And would you please describe the process rework by PulseForge tools? Yeah, rework. That means melt. The soldering is melting by to rework the So do you have the real case? I mean the system, the tools applied for rework the solution.
Right. So for rework solutions, what we have been working on is ability to maybe rework like smaller chip components on a board that has multiple circuits on it, right? And if you have, if you want to be able to kind of melt smaller components without having to go through a reflow process where you have a high heat load on, let's say, BGAs or other types of components on there that are more expensive, what we have done is we can go ahead and mask the areas that you don't want to expose. So this is a pulse of light, right? So you can mask pretty much areas that you don't want with either reflective materials or with just a cutout from aluminum plate, and that enables us to just locally heat up the board. And we have done a lot of kind of investigations around reworking these components. Maybe it mostly has been smaller components around larger components that we really don't want to heat up. And I mean, it's definitely feasible to use these tools as a reworking process as well. For the rework process, we definitely recommend the batch setup though, not necessarily the STP line for that.
Okay, thank you. Yeah. 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 Thank you. Yeah, Vahid. I think this is good presentation. Let me know if someone else raise their question. 各位贵宾有没有什么问题呢？ Okay. Yeah. Thank you. Yeah.
Team, everybody should have my email address. It's vahidakhavan@novacentrics.com, and I'm happy to answer any questions that come up in the future. So please reach out to me, and we'll try to get answers to you or anybody else in my team, and we'll get answers to you as quickly as possible. Thank you.
Okay. Thank you. Yeah. Thank you, everyone. Yeah. Have a good day.
Thank you very much, everybody. Bye-bye. Have a great day and success at this show.
Okay, thank you. Yeah, everyone is successful. And keep away from the COVID-19.
Yes.
Okay.
and keep
Okay,
safe, everybody.
Yeah, thank you. Hope next year you can join us Semicon Taiwan 2021 next year.
I look forward to it.
Okay, thank you. Yeah, have a good night. Have a good day.
Thank you,
Bye.
everyone. Have a
Bye-bye.
good day.
Yeah, Enrique, have a good day.